So this is the second part of Sprint 9, or the final sprint. So we're going to go to the visualizer and then the math tools. So visualizer first. So it's a singleton setup, all set up properly now instead of like before it was real messed up. So we've got our registration broker, our instance, and then it has one unit box, one unit sphere, which are used to draw all the visualizer stuff. And then I have two commands for box, one for box, one for sphere. They both just have a color and a matrix to draw it. And then the visualizer registration broker, which keeps track of those two commands for me. As for the visualizer, so start off, I've just got our two graphics objects here, the sphere and the box. Since it's a singleton, we have our delete, which is called properly at the end, and I delete those boxes. Then we have a render collision volume, which calls the collision volume that I pass it, and I give it the color, and it renders that color. I use that to just render my two different volumes. So to start, we have our show B-sphere. So this can be used by the user to show a bounding sphere on something. So you give it a bounding sphere that they are using and a color, and it will set up the show sphere it'll set up where the matrix to draw that, and it will call show sphere. The same goes for show ABB, which just shows up the sets up show box, as well as OBB just sets up for show box as well. Show marker creates a small sphere at the position that the user passes in with the color. So same thing goes, sets up a matrix and passes the color for show sphere. Line, give it a start and end point, and then the size of the line, so how thick you want it to be, and a color. And this creates a box with the correct matrix and the color they want. And simply show box and show sphere just create commands for those boxes or spheres. And then draw box, which is called by the command, simply calls for the box, it gets the box, sets up the color, the position, and then renders it to the current camera. Sphere does the same thing. And then we just have a process elements, which is called to process all the things that need to be visualized. For the user's end, there's also a setup inside of all of the collision volumes. So, for example, in the sample ship, if the user wants to draw the collision volume of the OBB for this ship, instead of having to say OBB visualizer, they can simply call the visualizer and tell it to render the collision volume on its collision volume. So this would not change if they changed what kind of volume it is. This simply takes the collision volume, and I think it was up here, it takes the collision volume and calls render on that collision volume. So all the collision volumes have a setup so that it can automatically just call the correct. I can't talk and look right now. So it will call the correct visualizer. So in this one, for example, if the render gets called, it simply just calls the visualizer to show an ABB. So just to make it easier on the user. So nice and easy there. Otherwise, everything's done through commands. I'm only creating these two graphics objects to show you the commands that I'm using. The visualizer just has the registration broker, which just has the execute commands like every registration broker, and then the draw sphere command, which calls draw sphere on the visualizer, and draw box just calls draw box in the visualizer. So pretty easy stuff there. And that call the draw draws all of them from the visualizer. Deletion wise, I mean, obviously you can see it works, and I've been using it the whole quarter, so it works. Deletion wise, visualizer is being deleted properly at the end when I close it. Yeah, that's about it for the visualizer. Next, I'm just going to go over the math tools. So for the math tools, we've got a lot of stuff now. I'm just going to walk through them in here. So first is just intersect BS, which takes two bounding spheres, so it just does the intersection between two bounding spheres by calling the point and distance function, which is below. Intersect ABB does the same thing, calls test interval for the two ABBs. So this is ABB versus AB, OBB versus OBB, or bounding sphere versus bounding sphere. Then we have the ABB versus a bounding sphere, since these are the first ones we did. Next is an OBB versus an OBB, an OBB versus an ABB, which both just call the same thing. And then an OBB versus a bounding sphere, which just gets a clamp point and then does the OBB, or the bounding sphere math right here. So we have a get min, which returns the minimum between two floats, a get max, which returns the maximum between two floats, test interval. So this is used for the ABB. So it takes the max and the min from the ABBs, and then it tests if if the min is less than the max and the x, and then the y and the z, and other way around to test if they are colliding. So that's just the ABB math. Clamping just takes a number and then a max and a min for that number and clamps it in between that max and the min. This one is for floats. I have another one for ints because for cells, I didn't want to have to convert the cell index to a float to do this math and then back to and make more sense. Just make another one that uses ints instead. Then there is a clamped point, which is once again same thing, just uses my clamp from above for each x, y, and z, and it clamps it in between a min and a max point and returns that point. Points and distance is for the bounding sphere stuff. Takes 2 points and a distance and checks if those 2 points are close enough within that distance. The get mid point just takes 2 points and gets the point in between them, or the center. Distance takes 2 points and gets the distance between those as a float. The calculate projection calculates the projection between on a vector from a bounding box's base based on its half diagonal, and then calculate projection D is the distance between the two centers onto that vector, so center A and center B. Test projection overlap does the test for if the two bounding box bases are colliding on a certain vector that it is being projected onto. So that returns true or false if they are colliding or not. This is just the test all projection overlaps, which takes the two bounding box bases. So this is for ABBs versus OBBs, or OBBs against themselves, and it just calls all 15 of the different vectors that it can be. Test ray against triangle takes the 3 points of a triangle that have been determined from a function in the terrain and take a point, and it then checks if that it finds the point underneath on the terrain, the exact point on the triangle that it is colliding with, and so you can get the exact point on the terrain using this function, and it returns that intersection point, or it returns the point that you gave it if it is not colliding. There's the terrain cell versus an ABB, which just calls test interval with the max and the min of the ABB, and then the max and the min of the terrain cell. Same goes for bounding sphere, just does the clamped and the points and distance with the terrain cell data, and for OABB just gets the correct data and calls test all projection overlaps with that AABB that is for the train cell and the OBB that is passed in. So that is all of my math tools. My math tools, they are all consts, so that it's all it's all the right way. It's fast, static. I mean, just a lot of math. So got all that. There's a little duplicate code that I could think of creating in here. So a lot of, as you can see, I was going over a lot of them. Use the other functions. So like get the max, get them in. Or sorry, that's something else. But using a lot of like clamped, using clamped, and obviously like the OBB stuff uses a lot of its own functions inside of there. So try not to duplicate code. Other than that, yeah, that would be the math tools that I've created, as well as the visualizer updated.